Swayam Prabha. Digital India. Educated India.
We'll start a new topic on numbers. By numbers, I mean integers. So the set Z, the infinite set of integers here consists of all the positive integers, negative integers, and zero. I'll use n to denote a set of natural numbers, which for us means all the non-negative integers. So it includes zero, and z plus would refer to all the positive integers. So some of this notation, like n, is used in different ways in different textbooks and sources. So for us, this is what it means. N includes zero and positive integers. Okay, and we'll also take for granted that these sets come with operations, addition, multiplication, and subtraction. And you can also assume all the basic properties of these operations, like commutativity of addition and multiplication, distributive property, multiplication by zero, addition by zero, and so forth. So these are basic properties that some of which would be part of an axiom system for integers, and the others are easily derived from those things. So we'll take those things for granted. However, we'll not assume that any higher level properties of things like prime numbers or properties about division. These we will prove. So what we're going to do today is start with something very simple. We'll prove something that I'll call the quotient and remainder theorem. It's a very simple fact. So let me get started by first defining divisibility. So for any integers n and d, I will say d divides n. So that's a notation using a bar in the middle. So d divides n if there exists some integer q such that n can be written as a product q times d. Okay, so this would also be referred to as n is a multiple of d, or that d is a divisor of n or a factor of n. Okay, so all of these refer to the same fact that there is some integer q such that n is equal to q times d. So here is a quick example. I'm going to take a number like 12. This is what its multiples look like. 0, 12, 24, minus 12, minus 24. So it stretches to both sides of the number line all the way to infinity. And it's a pretty simple structure. You could also look at the divisors of 12, which happen to be 1, 2, 3, 4, 6, and 12 itself, as well as their negative their negatives. Okay, and that's all the divisors of 12. It's a finite set. Okay, you can. That's just an example. There's one example that is special though. That is multiples and divisors of 12. So, of 0. Namely, and what is special is that, since 0 times anything is 0, so the multiples of 0 are only 0. You multiply 0 with any q, you'll keep getting back 0. So multiples of 0 only consist of 0. And on the other hand, every number divides 0. So you can take any d and take q itself to be 0. That 0 is indeed of the form q times d. So every integer d is a divisor of 0. So every d divides 0, whereas 0 divides only itself and no other number. We'll have, we'll use a lot of simple properties about divisibility that, you can usually use without proofs, but I will actually go ahead and prove them here, starting directly from the definition. So these are properties you would later in a quiz. So it's something you could use just by referring to it. But these are all simple facts that we do want to prove based on the definition we had. So let me just go through them quickly. So this is if m divides n, then m divides n times n prime for any integer n prime. And why is that? So m divides n means there is some q such that n is equal to q times m. And I multiply both sides by n prime, then I have n times n prime equals m times q times n prime. And if I just call this q times n prime q prime, which is another integer, I have n times n prime equals q prime times m. So this is by definition m divides n prime, right? So m divides n prime. So so we have that m divides n prime. Here it says if m divides n and n prime, then m divides their sum. And again, this follows from, again, write down n plus n prime, and you'll get it as q plus q prime times m. And since q plus q prime is some integer, which I'm calling q double prime, again, this means m divides this thing, m divides n plus n prime. The next one says if m divides n and n divides n prime, then there is a transitivity kind of property, m divides n prime then. And again, it follows easily by writing n as a multiple of m and n prime as a multiple of n. And if you substitute this n as qm, you get n prime as qq prime times m. So m divides n prime. The next one is a cancellation property. It says that if mn prime divides nn prime, where n prime is not 0, then you can just cancel off this n prime from both these numbers and conclude that m divides n. And that follows from cancellation property of multiplication. So you just start off by saying, okay, mn prime, if it divides nn prime, I can write nn prime as q times mn prime, and n prime not equal to 0. And the multiplication operation is such that it allows me to cancel off these non-zero factors from both sides. So I'll get n equal to qm. So this is a property about multiplication that we are using here. And we conclude that indeed m divides n, right? M divides qm. The last one, if you remember, we saw in our example, all the divisors of 12 were in the range plus minus 12. Okay, so that's what this is going to prove, that if the divisors of n, so number m that divides n, it has absolute value less than or equal to the absolute value of n. So why is that? So suppose m divides n, so n is equal to qm. And this is, of course, only for n not equal to 0, because divisors of 0 are all over the place. Every integer is a divisor of 0. So if n not equal to 0 and n is a multiple of m, firstly, I rewrite this or I derive this equation here by taking absolute value everywhere. So absolute value of n is absolute value of q times absolute value of m. And since n not equal to 0, I know that this q cannot be equal to 0, because if it were, then n would be equal to 0. So q is a non-zero number, and the absolute value of q is therefore greater than or equal to 1. And I use that to say that, okay, this n is, I can take an m out of it. I can write it as m plus q minus 1 times m, where this q absolute value of q minus 1 is something non-negative, right? It could be, if q equal to 1, absolute value of q equal to 1, it could be 0, but otherwise it is positive. So in any case, it is non-negative. So this quantity here, q minus 1 times m with absolute values, that's a non-negative number. So this whole thing is an absolute value of m plus something non-negative, so it is greater than or equal to m. All right. So this is basically just saying that this multiple of m that you're looking at, it is at the very least it is m. It could be bigger, 2m, 3m, whatever, but it is greater than or equal to m. Okay, so that's what it's saying. The multiple is at least as big as the divisor in absolute value. Okay, so that's also a useful property. All right, so now we will go ahead and prove the theorem that I promised you, the quotient and remainder theorem. It's a very straightforward fact you would be familiar with already, but we'll see a proof. So it says for any two integers m and n, where m is not equal to 0, but n could be anything, and both of them could be negative, or and it says that we can write n as in the form q times m plus r for some number r which is in the range 0 to absolute value of m minus 1. So it's a non-negative number, so we call it the remainder. And q we can call the quotient if it exists, right? And what the theorem is saying is that indeed such q and r do exist, and they are unique. There's only one way you can write n in this fashion for when you insist that r falls in this range. Okay, so let's prove this. First, I will prove the existence. So there is at least one q and r, and then we'll prove it's unique. And for existence, I will first prove this for non-negative n and non-negative m, right? So non-negative m in this case means m greater than 0 because m is not equal to 0. And what about the other cases? Because the statement is for all integers mn and not equal to 0. Well, the other cases you can derive from this by looking at this version with absolute value of n and absolute value of m instead of n and m. If n and m are not both non-negative, you just take their absolute values. You can apply the theorem for the non-negative version of n and m, and then from that, how do you derive it for the other cases? So here, let me quickly go over it. So if n is still non-negative, but what if m is negative? Well, then it's easy. Just apply the theorem to absolute value of m, which is minus m, and you can write n as q times minus m plus r. But q times minus m is the same as minus q times m plus r, and r here is indeed something that satisfies the condition that it's between 0 and m minus 1, absolute value of m minus 1. So you get you get your remainder to be the same as r, and the quotient is now minus q. What if n is negative? Well, in this case, there's a little more work because I can start off by saying n is negative of absolute value of n, and then for absolute value of n, I substitute this qm plus r. Here m is positive, so I just wrote it as qm plus r. But the trouble is you end up with minus qm minus r. And minus r may not be a valid remainder because originally r lies in this range, and say if it is positive, then minus r is a negative number, and that is not that's not okay for us. So in that case, what we'll do is actually instead of r, we'll take m minus r to be the remainder. So I add and subtract m here. So I added m here, I subtracted m so that I got minus q plus 1 times m. Okay, and I'll take minus q plus 1 as the quotient and m minus r as the remainder. That is if r is strictly positive. If r were already equal to 0, then minus r is also equal to 0. So then I would just take r to be, I would just take the quotient to be minus q itself. But if r is strictly positive, then I would take the remainder to be m minus r. And in that case, so when r is strictly positive, m minus r is strictly less than m. And remember, r is strictly less than absolute relative m. So m minus r is greater than or equal to 0. In fact, it's greater than 0 in this case, and it's equal to 0 if r is equal to 0. And the last case is similar when m and n are both negative. I can rewrite it, and here again I need to add and subtract an absolute value of m to both sides, so that my remainder is now absolute value of m minus r. Okay. All right, so what remains to be shown is the case of non-negative m and n. And I will fix any such m not equal to 0, and then prove the statement for all non-negative n. And I'm going to use strong induction on n. So what I'm going to do is something pretty simple, but let me stick to, since we just did induction, let's go over it in kind of some detail. So as base cases, I'm going to use all the n in the range, in this range actually, right? 0 to m minus 1. And in all these cases, I'm going to take r as n itself and the quotient as 0. So the remainder is n itself and the quotient is 0. And this is valid. There's a valid remainder in particular because it is in the correct range. How about larger values of n? So, I'm going to prove this for all k greater than or equal to m. So I'll prove it for k. And my induction hypothesis is that for all n strictly less than k, this holds. So it's a strong induction hypothesis for all n such that n less than k, the claim holds, namely there is some quotient and remainder with remainder in the right range. And be careful here that the range here matches up with the base case. And indeed, the very first thing I'm trying to prove here, k equal to m, right? My induction hypothesis only requires that it holds for n strictly less than m, which I have already covered in the base case. So this is fine. And how do I prove the, so again, assuming this claim holds for all n strictly less than k, I want to prove that it holds for k. So, so let's take k and write, and subtract an m out of it and get a number k prime. Now the point is, since k is greater than or equal to m, when I subtract, I'll still get something non-negative. And of course, it's strictly less than k. So I can apply the induction hypothesis to it and write k prime as a quotient and remainder with remainder in the right range, right? So remainder in this range, 0 to m. And my new quotient and remainder are going to be, in fact, my remainder is going to be exactly the same. And the quotient, I just need to take the quotient of k prime and add 1 to it. And that would work because all that happened is k is k prime plus m. So if I add 1 to the quotient, I'll go from k prime to k. Okay, so that's a simple induction argument. And in fact, sometimes it's also called the division algorithm because it's not a very efficient algorithm, but if you unroll this inductive argument, all you're doing is going from k to k minus m and k minus m to k minus 2m and so forth until you hit the base case. What you're left with is something strictly less than m, and that you take as a remainder. Okay, so it's giving you a way to compute the quotient and the remainder by subtracting, keep subtracting m until what is left is strictly less than m. And the number of times you did this will be your quotient, and what is left will be the remainder. To finish the proof, we need to also show that this quotient and remainder are unique. Namely, there are no two different ways you could write the same n as, you shouldn't be able to write it as say Q1m plus R1 as well as Q2m plus R2 unless Q1 equal to Q2 and R1 equal to R2, right? So the claim is that there is only, whenever, if you can write it this way, it must be the case that Q1 equals Q2 and R1 equal to R2. Of course, the reason for this uniqueness is that we are insisting that the remainder falls into this range of m values, 0 to m minus 1. Okay, so how do you prove it? It's pretty easy, actually. So suppose you have these Q1 R1 and Q2 R2. And without loss of generality, say R1 is greater than or equal to R2. Okay, so then R1 minus R2 is firstly greater than or equal to 0. And also it is less than or equal to R1 because R2 is non-negative. So this is less than or equal to R1, which in turn is strictly less than the absolute value of m. So by the way, I'm talking about m being any arbitrary non-zero integer here, positive or negative, and similarly n is an arbitrary integer. So here I'm not, I'm done with looking at just non-negative values of m and n. This part of the proof is for arbitrary m and n. Okay, so R1 minus R2 lies in this range. But also R1 minus R2 from this equation here can be written as Q2 minus Q1 times m. So R1 minus R2 is a multiple of m, okay? Or in other words, m divides R1 minus R2. Now, remember from a few slides back, if m divides a non-zero number, right, then that number must be greater than or equal to m. So R1 minus R2 will have to be greater than or equal to m, which it is not. Which means, it's the absolute value of R1 minus R2, which is same as R1 minus R2, would have to be greater than or equal to m if it were a non-zero multiple of m, right? If m divided R1 minus R2. So since that's not the case, R1 minus R2 is not greater than or equal to m, it must be the case that R1 minus R2 is 0. Or said another way, it's the same thing. R1 minus R2 is a multiple of m, and it is in this range. So there is only one multiple of m that is in this range, namely 0. Okay, so R1 equals R2. And once you have R1 equals R2, from here you have Q1m equals Q2m. And m is non-zero, so Q1 equals Q2. Okay, again, that's a cancellation property of multiplication. All right, so that proves that this quotient and remainder are unique. So the proof is actually pretty straightforward. What is interesting is just the fact that it is stating. So just as an illustration, let's take a case of m equal to 7. And here are all the various possible values of n, right? So I start listing the integers, starting with 0 for now and going 1, 2, 3, and so forth. Well, for all of these numbers so far, the quotient is 0 and the remainder is n itself. This was our base case in the induction proof. And we can keep going, but this second row of integers there, the quotient is 1, and the remainder is decided by the column they fall on, right? So as you so when we did the induction proof, when you subtracted 7 or m from an integer, say here n 10, you go back, you go one row up, but stay in the same column, right? So the remainder doesn't change, the quotient goes down by 1. So that's how how the inductive argument proceeded to, right? So the remainder will be given by whichever column you're falling on, that never changes, and the quotient is decided by the row you fall. And you could actually look at what happens to the negative integers also in this calendar, as it were. And so I just kept writing, backwards from 0. So it's again, it's the same thing, right? The the column decides the remainder. So if you take a number like -4, you can write it as -7 plus 3, right? So that plus 3 is the remainder in the range 0 to 6, and the -1 would be so -1 times 7. So -1 would be the quotient. So we have this table of width m. So for any non-zero width, you can write down this table and fill in all the integers to sit in this table, and the row index would be the quotient, and the column index would be the remainder. Okay, here's another example. If you took n equal to 11, the quotient is 1 and the remainder is 4. All right, so that's just a useful picture to capture this quotient and remainder there.